Okay, the floor is yours.
All right, thank you, Piotr. Thanks everyone for inviting me here and organizing this semester. In fact, it was a pleasure to come here a couple of times during this term. So I'll talk about the program of developing verification of quantum group invariants for three manifolds. And before I dive into theorems and definitions, which is going to be actually in the second lecture, I want to spend the first lecture sort of building background and explaining why the problem was complicated. As we say, if you don't learn history, we're bound to repeat it. So it's good to learn a lesson of what didn't work. And in math, we usually give talks on theorems that did work and things that are working, but we rarely talk about things that failed. And I think it's useful knowledge, actually, because sometimes students come to me and say, oh, why don't we try that? And I have to say, that already has been tried. So to prevent all these kind of questions, I'll try to basically review roughly 20 years of history and tell you how we got to a certain stage, what the questions are. And even later in the lectures, I'll try to be very honest and maybe that's a negative point of view, but emphasize things that still need to be done. So in fact, in the rest of the lecture course, I'll also give you not only homework, which is something easier that I know how to solve, but also I'll suggest lots of questions for actual research, something that, in my opinion, needs, some gaps that need to be filled. So therefore, this first lecture is definitely going to be kind of setting up the stage, reviewing the background, and formulating the problem and what works and how. So there is a connection between many different topics here. So that's another reason for me to have this lecture kind of as an organizing device. So first of all, there are knots, and then there are three manifolds. And some like knot invariants. And then there are also three manifold invariants. So these are usually close cousins and closely connected. So if you study knot invariants and this is your primary focus, then actually you can get very often to world of three manifolds, which may seem slightly more complicated and maybe harder to visualize, by a device called TQFT. This stands for topological quantum field theory, where as you produce three manifolds via surgeries on knots, we'll talk over links, more generally we'll talk about it later, you can basically construct three manifold invariants. So in this way, you basically have nice correspondence, and often if you have one type of invariant, it's natural to ask what is its counterpart. So in the world of quantum invariants associated to quantum groups, that's what I'm going to be talking about, this is usually a topic of advanced quantum algebra or quantum topology course, and it doesn't come early, but the punchline of this relation is extremely simple. In the world of quantum invariants of knots, the most important thing is color. So if you have a knot, in order to compute its invariant using quantum groups, you need to decorate the knot by some additional data. I may change notation for it, but for now I'll just call it lambda, so lambda will be color. So it's a representation of a quantum group, whatever your quantum group you're using, and it has to be allowed in a sense that, again, we'll discuss later. For instance, if your quantum group is just UQ of SL2 at some root of unity, so I can draw a picture of the unit disk in the Q plane, and these are roughly roots of unity. This is the origin. So if your Q happens to be exponential of 2 pi I over k, then the range of lambdas, so you can think of lambdas as finite dimensional representations of this quantum group, but unlike classical quantum group where dimension can be any number, so it could be a two-dimensional, 150-dimensional representation. In the world of quantum groups at roots of unity that people use most of the time, for example, in context of Reshetikhin-Turaev invariants, this lambda is limited in range, so it depends on your notations, but I'll just say that it's a number that varies from 1 up to k. Most important part is that it's truncated by k. Okay? So, yeah. Then, in this relation, coming back to connection between knots and three manifolds, most important part is summation over color. So this is very simple but conceptual point. So in order to get three manifold invariants, which, I mean, not can have a decoration, but three manifold, if it's a closed manifold, has no boundary, nothing else, then it shouldn't have any decorations. And the most natural way to get rid of this additional data is just average over it. That's what sum is doing. So sum over colors is what gets us into a world of three manifolds. There is also geometry involved in this discussion, so we'll probably come back to it at various stages, but let me mention maybe one more thing. You can think about, here when we go from knots to three manifolds, what we do the operation of cutting and gluing, and the Sergei operation that will show up probably not only in my talks. And if you do surgeries on knots and links, tubular boundaries, neighborhoods of these components have boundaries which are all tori. So you need to do cutting and gluing along tori. So a natural thing in the TQFT language is to ask, what is the Hilbert space or space of states of this TQFT on a two-dimensional torus? And what I'm saying is that in the context of quantum group set roots of unity, the space is k-dimensional. So for SL2, for example. So in particular, you can also realize the space geometrically as a space of holomorphic sections of a certain line bundle, L, over the space of flat G connections on the torus. Okay? More generally, if you wanted to construct this space for general genus G closed surface sigma, you would put sigma here. Okay. Interesting thing about the space is that its H2 is Z, is one-dimensional, so all line bundles for, in fact, for any genus on the space are characterized by a single number, its degree. So L is characterized by its degree, and this number is exactly K. So something that appears here as a root of unity, or what truncates the color, which sets upper speed limit on a color, appears in this picture as degree of this one. So the reason I mention this is this space is compact and may have a chance of having finitely many such holomorphic sections only if the group G is compact. So later on, we'll move on to the case where we'll try to replace compact group G. So in this case, for instance, it's SU2 associated to SL2 quantum group. But if I wanted to promote it to something like SL2C, I would immediately run into trouble because this would be non-compact space and it would just have infinitely many holomorphic functions and sections and so on. So that's something to keep in mind because in this operation, when we go from knots to three manifolds and perform this cutting and gluing operations, this is basically bread and butter of quantum topology, we have to ask, or one of the most important questions to ask, is this summation finite dimensional, finite or infinite? So most of the time until recent years, the focus was on finite sums. So that's why it was good to start at the root of unity where we have this bound, and as a result, we would produce some nice and concrete expressions. For example, here I'll give you an example of WRT invariant for one particular class of 3 manifold. You probably can guess which one it is. And it has the following form. So it's K over 2, G minus 1, sum over J from 1 up to K minus 1. Or in my notations, I think it should probably be something like K sine pi J over K to the power 2 minus 2G. So as you probably guessed while I was writing this expression, so it depends on two things. It depends on K, so K is order of the root of unity, so that didn't change. So it's exactly this number that we pick, or the truncation on color. But it also depends on G, and in fact, the answer I gave you is for a class of manifold, which is precisely S1 cross sigma G for general genus. Most importantly, you can see here that, yes, we do have, in this way of writing it, sum over something J, but now I hope you will always remember that sums that you see of this kind means summing over color of the node. So, or representation or color, and that's this sum here. Okay. Is this clear? Any questions? I don't know how much background I'm supposed to assume, so this is supposed to be slightly more advanced set of lectures, but nevertheless, feel free to ask questions. This is structure of WRT invariants, and relation between, what I'm explaining is the relation between not invariants and 3 manifold invariants. Again, this paradigm is very general, and what I'm trying to emphasize is most important thing here is color, which is being summed upon the separation. So far, so good. The fact that there are no questions worries me a little bit. It means it's either super clear or super mysterious. Okay, I'll continue.
Maybe for students who had said that this we turn something into life invariant or something like this, you just load letters.
Yeah, so this is, this W is Witten, R is Reshetykhin, and T is Turet. So, again, this paradigm is very general, so therefore...
It's the same with TQFT.
Huh? Okay, that's actually not a bad idea. So, topological, quantum, filtering.
And the last one, universal enveloping.
This one. Yeah. I don't think I'll do that with your permission. I'll just call this quantum group. It's a certain deformation of universal enveloping algebra, but it doesn't actually. So this emphasizes how it starts its life. But these days there are so many ways to construct it. And it doesn't actually have to start its life as deformation of universal enveloping algebra. So for this reason, I'm not going to put it on the board. But this is a good question. So any other questions? Again, don't be shy. We have lots of time. It's important that you understand.
So I can kick off the questions. Just one random one. If G is 0 here in this formula, for Reshetykhin into Raya, then K, it's 2 over K, the first term. So sigma 1, S1 cross S2. Just wondering that dependence on k, if it is numerator or denominator, changes significantly, or like a polynomial if g is at least 1, and then it's
right. So when
or is the formula
right, so there might be somewhere a factor of 2 or something, but it should be such that when g is 0, it's sometimes this formula applies really well when g is 1 or greater. So 0 is slightly more interesting, but in this case, the answer should be equal to 1 when g is equal to 0. So in fact, let's write it down. So when g is 0, this WRT, in that case, S1 cross sigma g is just S1 cross S2. It should be 1 for every value of k, independent of k. So this suggests that there might be some small changes here. For instance, it's easier to remove this -1. Actually, maybe not. Sorry. No, I think it's fine. Yeah, sorry. I think it's fine. Yeah. That's yeah. So it's actually non-trivial. It has to. Yeah. So those of you who have laptops open, try to put it on the computer, and then indeed, as Marco points out, this k will migrate to the denominator, but you summing over roots of unity. So it's a simple high school identity that this is actually equal to 1. So. You'll have to navigate trigonometric functions. Very good. I'm glad you asked this question because I can use this example in a minute then. So, any other questions? So then what do we want from categorification? We want to take this picture and lift it. This is wet. Yeah,
But the other one is it's not as wet.
yeah, thank you. But I think it's fine. I'll manage. So, well, that's okay. Right. So what we want is enhance this diagram by further step. So to produce this categorification. That takes us to the world of 4 manifolds. So 4 manifold invariants. That's basically the goal. And you can do it actually at both levels. So at the level of not invariants and at the level of 3 manifold invariants. So what categorification does, it takes, so in general, TQFT that is defined on d-dimensional manifolds assigns to d-dimensional manifolds numbers. But if you manage to categorify this, meaning promote numbers to vector spaces, they start looking like what TQFT in dimension d+1 should associate to your manifolds. So that's why the number changes from 3 to 4. And you should think of it as adding 1 extra dimension to your story, quite literally. And here, if you add 1 extra dimension to knots, what we're talking about is now surfaces. So we can study this sort of cubordisms either between 3 manifolds or knots. In this case, this is perfect for concordance and so on. So yeah. There is embedded surfaces. I say embedded because just like knot lives inside R3 or 3 sphere, this cubordism or concordance that I'm drawing here lives in some ambient 4-dimensional space, which is again R3 cross additional direction or S3 cross additional direction. So at this level, in the past 20 years, there has been a lot of progress, good progress, and that will be the starting point. So the question is, what about categorification of 3 manifold invariants? For instance, here we have all kinds of colored Jones, Homfley polynomials, and so on. By now we know how to categorify them. And the question is, well, again, I explained to you that producing TQFT is relatively easy, and very straightforward, so this has been developed, just summing over color. So natural thing is to ask, okay, can we lift this side? But before we lift it, first issue becomes that we usually, by categorifying, we mean promoting numbers, integers, to dimensions of various graded spaces. And here you can see that it's not going to fly because the way my answer is written, there is no integrality inside. Okay? In fact, when we categorify this story with polynomial invariants, we usually have expressions which look like q to the 5 minus 17q to the 9 plus blah, blah, blah. So coefficients are integers and they're written as polynomials in Q. Or perhaps series in Q but with integer coefficients. So here, Q is related to our K by the formula that I showed you in the very beginning. It's still here. And think of it that K is roughly log of Q, right? So if I look at this term, I see log of Q to some power. This is not really ideal for categorification. Here I have a sum which has upper limit until K, and this was a good thing. It was intuitive from the viewpoint of summing over colors, so that's exactly where the sum originates. But I cannot just write an expression sum of something up to log of Q as an upper limit of the summation. This makes no sense. Well, this is the only good thing, because sine of something divided by K does look like, say, Q to some power minus Q inverse power, blah, blah. Okay? So therefore, for purposes of trying to categorify, we were kind of in a very different situation in the world of knots and three manifolds. Even though this bridge is well traveled, this connection is extremely well studied and understood, there is nothing mysterious about it. I'm trying to highlight the conceptual components of it. The sides are quite different for purposes of categorification. Okay? So therefore, it's super exciting. This is a nice, beautiful picture and dream, which belongs to Crane and Frankel from mid-90s. So maybe I should put it here. Crane and Frankel, Igor Frankel, propose this sort of picture. But for this, we need to present our answers in the form which looks like this, which looks like some expansion in Q with integer powers and integer coefficients. And then we can start doing, or hope to move on to next step, which may be super hard and complicated, but until we're here, there is nothing to talk about. And again, I urge you to rewrite this in terms of Q. Okay. So many people back then threw their hands up in the air, and basically we were stuck. So it was not clear how to proceed back then, meaning in late 90s, early 2000s. However, there were a couple of developments which indicate some sort of progress. Maybe I can erase this now. So some insights came from physics. Which was useful in early stages. In the rest of the lectures, I'll try to not rely on this in any way, but it's actually good to know what happened there. And many physicists in mid-90s, for completely different reasons, their reasons were motivated by connection of knot invariants to enumerative geometry, either quantum geometry, where you replace your space of functions by non-commutative deformation thereof, or connection between Gromov-Witten invariants and various knot invariants and three-manifold invariants. So they managed to come up with interesting integrality properties. So they found integral structures in our traditional knot and three manifold invariants. And from the viewpoint of enumerative geometry, this is not terribly surprising because they were trying to study counting of something. That's what the word enumerative stands for. And these people include Gukov and Waffe, Sinha, Waffe. Actually, the list is very long. It does involve, at various stages, Waffe and his many collaborators. Maybe I'll also mention Sebastian de Haro, since these are some less known papers these days. So what they proposed the following. They proposed a way to write the WRT invariant of a three manifold. So along the way, by the way, in this first lecture, I'm fixing notation. So for me, three manifold will be M3. That will be opposite from how it's used in Donaldson type theory, because X and Y will be reserved for some varieties. In mirror symmetry, X and Y are usually used for mirror varieties, so I'll come to that. And therefore, here I need to use M. So M3 is a three manifold. So they managed to write it as a limit of as Q goes to e to the 2 pi I over K, this root of unity, which the Witten-Reshetikhin derived invariance depends on the root of unity, of some auxiliary function, I'll call it Z. For them, it had a meaning of, again, counting something. So this is usually called either Gopal-Kumar-Waffe or Donaldson-Thomas invariance. I'll use DT, for example, which depends on M3 and Q. And they managed to produce this for certain class of three manifolds. In fact, for length spaces, for S1 cross sigma G is pretty much the list of examples that they studied. And for either physicists in the audience or those of you who are curious about what physics words go into this, I said these are insights from physics. It involves a study of so-called five branes in 11-dimensional M theory that are supported on a 6-dimensional manifold, which is of the form S1 cross R2 cross your 3 manifold. So it's, again, if you like physics, this may be useful to you. If you're curious, then this still may be interesting. Otherwise, this is a fancy name that you can use to show off with your friends. This is where it comes from. In any case, it suggests that quantum groups have something to do with it. And here we actually can anticipate that this should be quantum groups a generic Q, because what they managed to produce is an actual function. So I want to emphasize that their answer was an actual function. So it had independent definition, which they implemented and computed in a couple of examples, that produced a function of Q at a generic point here. And then they basically send Q to the suitable root of unity and recover WRT invariant. Okay? So in parallel, so this was late 90s, mid to late 90s, early 2000s, early 2000s. And in parallel, there were some experimental developments in math. So, experimental math. Where people said, let's try to guess. I mean, I actually don't know for what exactly motivation. Here there was some reason to do it. There, perhaps something quite different. They said, let's look for a function, f of q, which has this property. Okay? So, I don't think they cared about integer coefficients because that was way predating the categorification program. So they didn't care if this function has integer powers, integer coefficients. They just asked, let's have f function. Okay. And so then this was basically also kind of experimental, but unfortunately it was really hard to get it off the ground. I was involved in this program myself, so I'll tell you again what the difficulties were. So for instance, we just studied, computed on the blackboard before I erased, WRT invariants for some particular class of manifolds, including S1 cross S2, which has WRT equal 1 at every root of unity. So now, suppose you are asked, you have value 1 at every root of unity, so what is the right function here, right? What would be your guess? Now let me ask you a question.
1 everywhere.
That's a good answer. Can somebody come up with a different answer? So,
function.
very good. Yeah, so Mr. Dedekind, so usually it's written in tau, but since I left Q for quantum, I'll write it in terms of Q, told us that there is this beautiful function which plays a role in analytic number theory and many other things. So in terms of Q, it's Q to the 1 over 24, and then this is early product form where we write it as product over I from I to infinity, 1 minus Q to the I, okay? So in this product, if Q is a root of unity, there will be a term, if Q is of the form 2 pi e to the 2 pi over k, there will be a term, and this is let's say j, so you don't confuse it with a square root of minus 1. There will be a term which vanishes. So therefore you can take any power of eta function. The other suggested single power, that's perfectly fine. So if I write f of q equals 1 plus, say, eta, that's okay. That's a function of q, and it doesn't change anything. In fact, I can put here coefficient, I don't know, 1 million. And nothing changes. I can play with coefficients, put it 1 million over 17. I can put here power 24, and things will work. So, of course, now I have a freedom. So, for example, 24 is a nice power because it will get rid of, again, integer power. It will, fractional powers and will make everything integer powers of q. So if I care about this for some reason, that could be good starting point. But again, back in the day, people didn't care about integer coefficients or integer powers of q. That was not a thing because it was way before categorification program. So the point in any case, with either this additional conditions or not, you have huge freedom. In fact, in math terms, you can basically add any cusp form to your answer. So it will do. So therefore, this produces two ambiguous story, and that was the difficulty, basically. That was the challenge. Nevertheless, a couple of people, usually Lawrence, Zagier, and Hikami are mentioned in this context. So Lawrence and Zagier, and also Kazuhiro Hikami. And this was followed by many others, including myself. We tried to basically play this game, and I don't think we had any systematic way of justifying any answer and produce what we called candidates for certain spaces. But again, these were not systematically computed from manifold point of view, from topology point of view. They were just guesses, to be completely honest. There was another thing that came here, which is probably more important, is not so much that, yes, it's true we didn't have systematic way, but luckily, thanks to these people, we started uncovering some useful structure. And structure is good because it can guide us, especially in the future, and that's what will happen in some of these lectures. So we started writing Q in several different ways. So already told you that Q is naturally First of all, for us, Q is going to be quantum parameter, and Q will appear in every single talk I give. So will be this is very central because we are talking about quantum groups. And from here, you already see that the attempt is to formulate something for quantum group at a generic value of Q. And so far, for instance, it was related to K by this relation. So you can formulate the problem of moving inside the unit disk as making K complex. That's actually fine. If K is general complex number, then yes, you can achieve this. But you can also write it as exponential of another complex number h bar, I'll come back to this, or another complex number 2 pi I tau, and the latter is more natural in theory of various modular forms and modular objects. So you can start asking questions, okay, if I have some kind of function of Q, how does modular group act on it? Okay. And this is actually the insight that these guys brought into the game. So people started kind of, as we produce something useful for topology or quantum algebra, people started asking questions, okay, does it, by the way, play any role? Can you recognize that it can iter there? So this was quite helpful. However, this physics inside is also not totally useless. So I'll write this as a two-dimensional disk. It's the same. Because you can ask, even back then, that was early 2000s when this was studied, where does this modular group SL2Z come from? So SL2Z modular group, which actually acts naturally on tau by fractional linear transformations. So it was suggested, let's do that, but when we ask, like, okay, can you expect SL2Z as, I don't know, group of autoequivalences of some category of a quantum group or something else, there was no such simple interpretation. So the origin of this, if your problem has a symmetry, first thing you should ask is, what is the symmetry in my problem? Where does it originate? Is it hidden or is it explicit? So here, luckily, it was explicit because, so that's, again, insight from physicists, and they also ask this modularity question. So notice that in this 6-dimensional geometry, 3-dimensional part is something that we care about, that's a 3-manifold, but then I introduced another 3-dimensional part, okay? And this other 3-dimensional part is actually doing the job somehow, and it's responsible for quantum groups. So sometimes people even write Q here to emphasize that this is the part where quantum parameter comes from. But topologically, it's a solid torus. It's S1 cross 2-dimensional disk. And boundary of a solid torus is the usual elliptic curve, or 2-dimensional torus, and the mapping class group of this T2 is precisely SL2Z. So, therefore, you may not pay attention to what physicists tell you, but then you'll be oblivious to various interesting effects. For instance, sometimes as story evolves, and I'll show you examples later this week, the correct group of symmetries is not SL2Z, but some congruent subgroup. For example, gamma 0 of 2, gamma 0 of 4, and occasionally you see more exotic choices. So from this point of view, when in a perspective where origin of SL2Z is manifest, you can immediately ask yourself, what is the right choice? And again, if you speak physics language or if you have physicists among your colleagues, they can quickly tell you from looking at the system, because here the symmetry is supposed to be manifest. Otherwise, you have to just make yourself a cautionary remark that sometimes your full symmetry or modularity that you're expecting is not going to be SL2Z, but some congruent subgroup of that. Okay? So this is something that is rather delicate, because spotting the difference between them is often non-trivial, but it becomes completely obvious in one perspective. So, okay. Okay, any questions so far?
Yeah, what are these gamma zero groups?
These are congruence subgroups of SL2Z. So SL2Z is a group you can think of its element as a 2x2 matrix. So with elements A, B, C, D, such that AD minus BC is equal to 1. So when one of the off-diagonal guys, for example, C is 0 mod 2 or 0 mod 4, you get the congruent subgroup. So this is subset of integral matrices of 2x2. Any other questions? That's a good one. Okay, so we moved to like early 2000s, and around that time, first of all, many people, including myself, proposed basically interpretation of homological knot invariance, categorification of quantum group invariance of knots in terms of similar physical setup. So we did it with Schwarz and Waffa. Also, Witten worked on the same thing often, and many other people, and we all kind of used the same system, so there was definitely clear agreement. So a natural question was, what would happen if you feed into that same setup, into that same construction, general 3 manifolds, possibly with knots? So that's exactly what I'm telling you about. So it would actually lead to precisely this, to this setup here. So then you might ask, okay, what prevented you from computing it? I mean, why didn't you do it, I don't know, 15 years ago? So honest answer is that's hard. From the physics point of view, this 6-dimensional system is highly complicated. I mean, we don't have nice Feynman diagrams to even start the calculation. So we need some clever tricks. So it took a while before some progress could be made here. And some part of the progress had to do with treating these two sides sort of separately. So this is a 3-dimensional part of the geometry, and this is 3-dimensional part of the geometry. And people, including myself, started exploring connection between what would the system look like if you focus on just this 3-dimensional part or this 3-dimensional part. So this is called 3D correspondence. And what we learned from those days is that on this 3-dimensional part, the topological theory on M3, the way it looks like basically complex Chern-Simons theory. CS stands for Chern and Simons. And complex means that our group now is complex. So compared to what I told you in the very beginning, we take G, say if it was SU2, we complexify it, and it becomes SL2C. Not to be confused with SL2Z that I wrote here. This could be related to symmetry of the problem. This is the gauge group. And this brings several things that are good and bad. Good things is that it allows you to work with general Q. So it allows you to work with Q, which is a complex parameter inside the unit disk. So this is where Q is just a set of that lives in complex numbers, maybe minus some small set. So that picture is very valid. That's a good thing. Bad thing is that, as I already alluded in the very beginning, your set of colors now is infinite in this theory. So if you study knot invariance and try to decorate your favorite trefoil, figure 8 knot, or knot with 15 crossings by some color, here in this theory you have a choice of highest weight. So if this is piece of a knot, by lambda can be viewed as, for example, highest weight of some representation, is now continuous complex number. So already from this, before we get into definitions and theorems, we should anticipate that whatever invariants we're going to build for this theory, if we'll succeed, they'll be integrals rather than finite sums. Okay? And it is making sense or defining this integral so that they're mathematically convergent and don't cause us trouble. That's actually where most of the work needs to go in this sense. So another byproduct of this 3D correspondence was the fact that perturbatively this theory can be defined as a formal H-bar series. And this produces invariants, I'll call it Z perturbative, of a 3-manifold as formal series in this parameter H bar, which already appeared on the board. And this actually can be mathematically defined. So this was studied in various contexts. In simplest cases, this is Otsuki series. In more complicated cases, you can define this using so-called quantum dilogarithm. And this was basically useful, but the problem is that it tells us what the answer looks like near this point, near the point q equals 1. Whereas what we want, and only in tiny neighborhood of it, but what we actually want is an answer which is some function of q, ideally with integer powers, integer coefficients, and when we write such an expansion, of course we expand near q equals 0, not q equals 1, where h bar small is. So we somehow need to transfer information from here, which was achieved in early 2000s, to this part. And this brings in a game yet another component which we'll touch. So this is done these days using part of complex analysis called resurgent analysis. And this is one of the kind of good lessons that came from this story. Right, so maybe I'll finish with conclusion that what I'll continue with next further is I'll tell you more about this systematic definition of this invariance, which is completely independent and they can be given its own meaning, their own meaning, a generic Q. So given a 3-manifold, we'll associate to it a Q series which achieves the job. But one big surprise here was that this invariant is labeled by spin C structures on 3-manifold. So it's not a single Q series. So that was basically the key component. It's a collection of those. And as such, at first, it was not expected that you should have spin C structures. People who loved quantum groups or the Stern-Simons, they never anticipated this. But in retrospect, it turned out to be a very good thing because if you ask what this does as a function of spin C structures, it actually connects very nicely to many other invariants of 3-manifolds which depend on choice of either spin or spin C structure. For example, if you go to Q equals I, you recover Rochlin invariance. If you go to Q equals 1, you recover derived torsion. So recently, Ras Ahmedchad, Slava Krushkel, and Peter Johnson had a very nice paper where they connected this object to lattice homology. So there are many things in Floer theory, in Higert Floer, where dependence on spin C structures is a good thing, and therefore this allows to put this quantum groupie fellow on the same close footing with Higert Floer type objects. So this, in retrospect, the dependence on this additional label is a good thing. So I'll stop here, and this was basically overview of where we're going to be heading. So my job starting tomorrow will be to go much more slowly and give you definitions and so on. So there's always a choice with lectures that either we move slowly and then you can ask, okay, where is this headed? So that's why I gave this first lecture to kind of give you overview of what people tried, and also now we'll see like where this whole thing is headed.
Yeah, we may have time maybe for one quick question. Okay, let's push them for tomorrow, and thanks Sergei again. We have a quick break and we resume at 11.